Hello, everybody. Welcome to our sixth lecture of numerical methods. This is going to continue our root finding operations looking at open methods rather than the bracketing method of last time. However, from last time, you should remember basic facts about root finding methods such as what are roots, why is root finding important, and methods like the bisection method and false position. We're going to transition away from these sort of bracketing method problems and move into open methods, particularly the fixed point method, the Newton-Raphson method, secant method, and inverse quadrature. After we go through the behavior of what's happening in the actual methods, we'll talk about some built-in MatLab functions for finding roots. So, as you remember from last time, a bracketing method looks at uses 2 points, a lower guess and an upper guess, right? And it moves back and forth between these by using the switch-in sign between the lower guess and the upper guess to determine, iteratively determine how we get closer to that root. An open method is going to change because instead of having 2 guesses, we're going to require possibly only 1 guess and 2 in some of our methods. But here's this method this figure is going to show. Instead of trying to bracket the methods, so having 1 guess on the left and 1 guess on the right, we're going to actually use extra information that we have about the tangent of that line or the derivative of that line to get better guesses. Although this is very important because it can be significantly faster than the bracketing method. However, it may diverge. What do I mean by diverge? Well, in this example, we can see as I move from xi to xi plus 1, and I move up this sort of triangle back down around, I end up getting closer and closer with every iteration to the actual root. Divergent methods or divergent behavior is when I move from one position, say xi, to the next position xi plus 1, and then that next step moves me farther away from that method. So instead of getting closer and closer to the root, I get farther and farther away. So the benefit of the open method are we can be faster, but we can end up having divergent solutions and end up having being able to find the root or ending up far away from the root that we're interested in. So let's look at this method in more detail. So sort of as I alluded to on the previous slide, the idea behind the root is open methods of the root is to use more information than just knowing whether a root is between 2 points. Rather, let's say we're starting at this xi point, we can use the information about the tangent of the position at that point. So say we're at xi, if we knew information about the tangent line or the derivative at xi, we could then project out a straight line with the slope of the tangent to find where that approximate root might be and use this as our next guess for x. We can then find the tangent at our new f of x value and then project that slope. So you can see in this open method, at least detailed here, we're able to get to that root in 3 steps. So 1, 2, 3. So much faster than before. Once again, with if we have a divergent solution, if we say take a guess where we sit a little bit differently on that line, say maybe back a little bit over here where the slope is much shallower, we can end up over projecting that position. And when I take that next guess or function evaluation as to what the derivative is at this point, it can end up shooting us off to the right instead of coming back to the left. So if that derivative, if we pick that new x point that sits on the other side of a maxima, we're going to end up with this divergent solution. And then we'll end up at some other point on the graph or never coming to a root at all. So we can see the benefits on the left, on the right, sort of walking through here. If we overshoot that tangent, we can end up picking a point that has that slope that's pointing away from the root rather than towards the root, and we end up moving farther away in divergent solutions. So let's take our first stab at an open method. So let's take a simple fixed point iteration. So what our plan is going to be is we're going to rearrange f equals 0 so that we get a single x on the left side of the equation. So we can get this x equals g of x. So a little bit different. When we do this, we essentially have x on the left and x on the right. So we're going to be able to form this sort of loop form. So we're going to guess an x, then we're going to calculate, we're going to take that guessed x, put it into that g of x equation, which will give us a new x, and then we're going to back follow that loop. Once again, we're going to look at the approximate error given by this equation from last time to tell us if we're converging and when to stop. Remembering from last time, we have the approximate error is the absolute value of xi plus 1 minus xi over xi plus 1 times 100% to put that on that percent scale. Let's say we want to solve f of x equals e to the negative x minus x. This may be difficult to solve by hand, or if we had a more complex question, may be difficult to solve by hand. But we're going to use our open method to solve this equation. Just for an example, I've plotted these points over here on the right-hand side of the slide. We can see here's that equation, e to the minus x. We can see the root that we want. And what we're really doing is we're splitting this e to the minus x into two equations, right? So we're going to put this into this g of x form. We move this negative x over into the other side to get g of x is equal to x equals e to the negative x. And what this is representing graphically is we're looking at the intersection of these two functions. So here we have e to the minus x, here we have x, and we're looking for where these two are going to intersect. So where this equation is true. So we're going to split this g of x equation up into our two different equations. f1 of x, which is just equal to x, so just this straight line, and then this f2 of x, which is exp to the negative x, that coming down. So we're interested in where these two are going to collide. So let's take our case and an example and say we want to find this root. So we don't know what iteration to start on, so we can just say, oh, let's just guess x equals 0. So if we're unsure, where that root might be, x is 0, maybe a good idea to start with. We're ready to go. So we can now take that x equals 0. Let me get my pen. We can take that x equals 0, and I'm going to put this out over here. We're going to first stick it into f2. So the reason why we're sticking it into f2 is if we stuck it into f1, we have x equals x, so that's 0, so that doesn't really get us anywhere. Let's stick it into f2. So f2 is going to be exp minus 0. So the exponent of 0 is 1. This becomes our new x. So if we look on this sort of graph, we started here, and then maybe we're going to move down to, I don't know, let's call this 1. So we're now sitting at this point on the graph. Okay, so now we can start calculating our errors. So we have 1 minus 0 over 0. We can just call this 100%. And then in this case, we know what that true error is. That's about 76%. But now that we have our new guess for x, we're ready to calculate a new value. So let's put in f of x2, sorry, f of x1 is going to be x equals 1. So we can come into our next guess. X is going to be equal to 1. We can now take that equation, put it back into x2. X equals exp negative 1. This ends up being this 0.369 number. And then we can start doing, oh, maybe that sits back over here. We can now take 0.369, plug that into exp negative x, which is going to be 0.6922. We can do that again to get 0.55. We can do this iteratively until we end up converging and our error is less than whatever we want our convergence criteria to be. Okay, so hopefully this is showing you we're taking these x's, we're plugging them into that x equals 2, setting that equal to x, and then we're just doing this again and again and again. So let's talk about convergence. We said before that some of these methods can diverge. For the simple fixed point iterative method to converge, the derivative of that g equation that we were just talking about has to be less than 1 near the root. What do I mean? So shown here in this example is a case where this slope is less than 1, right? If I draw this line, that slope is less than 1. Why this is important is because this is going to send our solution finding algorithm back towards the root. This will also work if our derivative is between -1 and 0. So once again, it's going to send us sort of in this spiraling inwards pattern. However, if I have a very steep slope of my g function near that root, so near that intersection point, I'm going to end up having a divergent solution because every time I move here, I'm going to have a number greater than 1. When I have a number greater than 1, x is going to grow. I'm going to get bigger and bigger and bigger x's moving away from that root. And then the same thing is going to hold if I have a derivative that's less than -1. So if the derivative has an order of has a magnitude of greater than 1, we're going to be in that divergent solution. So not one of the solutions that we're looking for. So the other method that we want to talk about today is the Newton-Raphson method. This is used in many solutions of chemical engineering problems, and we're going to hit it up again and again as we go towards throughout the course, particularly in multiple equations and then in later chapters looking at partial differential equations. Where this is going to come in is based on the fact that we can build, that we're going to know the tangent of that curve. So really what we were talking about at the beginning of class. So we're going to once again take our x, some sort of guessed x, find the slope, and then follow that slope down to y equals 0. So if I say I'm at this point here, I guess that dotted line, or I figure out what that dotted line slope is, that's going to then take me to the x equals 0 point. I have a new guess for my x. And now I can do this again and again and again. So you can see in this example, if I know what that slope is, I can find that root more or less in 2 steps. Let's put some numbers to this, or some equations to this idea. So let's first look at the definition of a derivative from calculus. Sorry about that. So we can see that the derivative at any point can be equal to the function value at that point. I'm going to say call that I, minus the value of that function at another point, so say I plus 1. So rise over run, so xi minus xi plus 1. Right? So just our general definition of a derivative or the tangent line from calculus. So we can look at these values and say we want to find these points, so this xi plus 1, where f of xi plus 1 is 0. So we can just rewrite this formula as fxi minus 0 over xi minus xi plus 1. And that's now our derivative. Okay. So with this formula, I can rearrange this to isolate the quantity that I'm interested in, which would be this xi plus 1. So if I take this bottom term, multiply it over on the other side, and rearrange, I can come up with the equation xi plus 1. So the next guess in my iteration is equal to xi minus f of xi over f of xi derivative. Okay, so this is going to be the equation for our Newton-Raphson method. Use our Newton-Raphson method to estimate that root that we had talked about earlier, right? So e to the negative x minus x. We're going to once again use this initial guess of x equals 0. Let's calculate what that derivative is. So f prime of x is equal to, what's the derivative of this? It's just negative e to the negative x minus 1. And so now we can take this equation, we can plug it into the Newton-Raphson equation itself to get our general equation that we're working with. Xi plus 1 is equal to xi minus that function value, so e to the negative x minus x over the derivative. We solved that over here. That's e to the minus x, negative e to the minus x minus 1. And we're ready to solve. So I can take that iteration 0. We can take x equals 0 and put it into this equation. So if I put 0 in, and I'm just going to do this for this one time, we've got xi plus 1 equals 0 for xi minus exp to 0 is 1 minus x is 0, so that's 0. We now have on the bottom negative exp to the 0, so that's would be exp to the negative x would still be 1, so minus 1 minus 1. So we get in total 0 minus 1 over negative 2, which is 1/2. I'm sorry. So for iteration 1, we have an x value of 0.5. Okay, so if I compare this to the true value, this is an error of only 11.8%. Right. So I can do this again. I can plug in my numbers. I'm not going to actually do out the math, but we have xi plus 1, xi is 0.5 minus exp negative 0.5 minus 0.5 all over negative exp negative 0.5 minus 1. When you do this out, we end up with 0.56631, which gives us a true error of 0.147%. So you can see at 2 iterations, we're already very, very close. I'm going to skip a few steps, but by the time we get to iteration number 4, we have a guess of 0.567143 and a true error of less than 10 to the minus 8th. So in using our Newton-Raphson method, in 4 steps, we have an error of less than 10 to the negative 8th percent. So we're getting very close to our solutions very fast. And this is going to make up the major pro of this method, right? So the error of the ith plus 1 iteration in general is proportional to the square of the error of the ith iteration. So we're converging as the square of the error. So we're getting smaller as the square function. Now this is in general, because sometimes we have functions that are going to show slow convergence or poor convergence, sort of shown here on the right. So places where the derivatives are very small or very low, we can end up having these very shallow slopes and can send us way out here, and we can get very wrong answers. Same thing if I maybe start here, I go down, I end up here, I can end up getting shot away from that route that I'm interested in. Or if I happen to find exactly hit a local minima, I can end up being shot very, very far out. Okay, so we have these benefits of being fast through the quadratic convergence of our error, if we're lucky. But sometimes we have these ill-performing materials. One of the problems, though, with the Newton-Raphson method is we have to know analytically what that derivative is. So we need to be able to plug into that equation an analytical expression for that derivative. This is often not the case, right? If we're just trying to come up with a general way to approach these mathematics, we want to sort of be able to tell the computer, here's an equation, I don't want to tell you anything more, figure out where my root is. In order to do that, we can use an approximate derivative. So instead of having an analytical solution to that derivative, we can just sort of guess what that derivative is. So we can do this by remembering that our derivative, right, is that f or derivatives are that rise or run that slope, and we can approximate that by taking these two differences. So maybe f of xi minus 1 minus the function value at the previous step minus the current function value over xi minus 1 minus x. So the reason why this is approximate, right, is because the derivative only occurs when the difference between these two go to 0. But this should give us a decent estimate for what that back derivative is. So we can take that equation that we had previously for that Newton-Raphson method, where we took our next guess is equal to the current guess minus the function value at xi over that derivative, and plug in this equation for our estimate of the derivative. Right? So when we do that, we end up with this equation. All I've done is I've taken this top equation, plugged it into the bottom for the derivative, and done some rearranging. So now we have an equation in this method that we're going to call the secant method, where the value, my next value, depends on my current value and information that I knew or know from a previous iteration, right? So we're using more and more of the pieces of information available to us. So let's sort of do a demonstration. So once again, we have our equation for my derivative, and I have an equation that I'm going to use for my estimate. So here I need two guesses, right? With the Newton-Raphson method, I only needed to know 1 point. Here I actually need the two. So if I take a guess at xi and a guess at xi plus 1, I now know these 2 points on this line, right? So I now know this piece of information. I know the difference between the two and those two pieces. Essentially, I can draw this line between the two of them. So this is going to give me the slope. And then from that slope, I can find where that's going to cross that y-axis. So now I have a new xi plus 1 and a new xi. So I can now draw a new slope line between this function value and that old xi. That will mark us roughly here on this graph. And then with that next solution, I'm more or less on that route. That method is very good. So the secant method is very good once we have two guesses, but we still require that two guesses. So we would have to, input into our equation what we want our guess to be. One of the ways around this is called the modified secant method. This is going to behave only requiring a single guess and then adding some small perturbation to it. We're going to keep the same idea of using that tangent, but instead of calculating this next xi, we're going to take our guess, so maybe this first purple line, and then add some small perturbation, delta x. So this distance between the two purple lines, maybe I'll erase that, between the two purple lines is going to be delta x. So because of this, I now have this way, I now know not only what is this difference between the two x's, right? It's delta x, it's that by definition, but I can also calculate my that function value at that next step by saying xi plus delta x, right? So if this is xi, then this is xi plus delta x. Right? So I can use this form of the equation now. I have 2 points between the two lines. I'm able to fit a tangent line. I can come over here, find where they intercept using this using this perturbed version of my derivative and plugging it into my secant method definition to find that next xi plus 1. So maybe call that here. I then can go up to my new position, that new f of x position. I can take, I can recalculate that derivative using a perturbation, and we can see roughly we get that root relatively fast. So I want to point out very briefly before I move on, the fact that even though in the second step, even though we have already points down here, we're still calculating the local derivative using that perturbation. The last method I want to talk about is inverse quadrature. So in the last few points, we've seen that by using the definition of a line and using the functional format of derivatives, we can get better estimates for the roots than if we just do, say, bracketing methods, right? We're using more information that we know about the system. However, we're only using 2 points, right? So we're using, say, these 2 points to to draw this line between the two, and we're getting an estimate. However, after several steps, we know much more about our system. There's a lot more information than just the current point and the last point. So can we use more of this information? Well, the simplest extension of this is to use 3 points to make a curve rather than just using 2 points to make a line. So can we make this parabola? And so can we use a parabola? And let's look, for example, so if we have these sort of 3 points here, I could fit a parabola to these 3. We can find this estimate, say here using that 3 points, and it's probably much better off than using just this line between the two. The problem with possibly using the parabola that you might see here is if I sort of draw the rest of that parabola out, there's 2 points, there's 2 roots for that parabola as it crosses the x-axis. So we need to think about a way around this. So can we still fit a parabola but only have one point where we're crossing that x-axis? If we fit our line horizontally, so instead of having this red-shaped curve, we can fit this black-shaped curve now that I'm highlighting in red to be horizontal. So instead of y equals f of x, we're going to fit x equals f of y, which we can do because we know these points anyways, right? And in this case, when we fit this horizontal parabola, we're going to be able to find a location where x crosses that, where x crosses the x-axis. So I'm not going to go through the derivation of this formula. We'll talk about fitting parabolas later in this class, but suffice it to say for now, we have this form of the equation where x of I plus 1 is equal to a series of slopes according to y's. I'm down here where each of those y's, yi, is equal to f of xi, right? And we know what that functional form is. Okay, so this is going to round out the methods. Inverse quadrature, right, should get us there even faster than the linear-based methods. However, it's going to require knowing more information about the system, right? Because we're using 3 points to fit a curve as opposed to using only 2 points to fit a curve. These functions, these root-finding functions, are so common and critical and widely used in engineering and math that MATLAB has built-in functions to help us find our roots. The first major one is called fzero. And so fzero is going to provide both some of our bracketing methods and our opening methods wrapped into one. And MATLAB internally is going to decide which of these functions are going to get there the fastest. So it has the formula where we input some, set the desired root out here. So x equals to f0, our normal function call. We then pass in our function, I'm using an anonymous function, into f0, and we give it our starting guess. Right? So we can pass in either a relatively simple function like we've been talking about f of x equals e to the negative x minus x, or we can have whole programs such as our water gas shift example. Big long programs that are going to take in multiple variables and have if statements and wrapped all together, and that can then be passed into that function call. Okay, so that makes fzero quite robust. We can also get a little bit more information from the set if we say by saying x comma f of x. So this is going to not only evaluate our tell us what the root is, but what is the function value at that root. So this will tell us how well converged it is. Right? We can decide to use or help MATLAB by going down the bracketing method route by putting in two guesses using this bracket function down here to sort of force it to go through a bracketing method. Right? Once again, we can either get out just the value or the value and the root. We can also pass different options to fzero. This may be if the function is going to some values that are going to be put into the function, or something that's going to be told to fzero, like how to display behavior. There's a whole bunch of different options. I suggest going and looking that up on the MATLAB website if you're interested, but some common ones might be setting offset and setting display so that you can see the number of iterations required to get to that value, or you could put in tol x, so to tell MATLAB how tolerant the solution should be, right? So you put in, you make this first function call that's going to be options. So you would say options equals optset. And let's say we want to change the tolerance. We can go in and put tol x in quotes to tell MATLAB that it's there, and then I don't know, maybe we only want it down 10 caret -3. Wrap that in the parentheses, and then we can pass that along. We can pass options along to fzero to be used in that call. So to show this as we want, here we have that example. We have x comma fx, so this is going to show us not only the root but the function value with that root. We call fzero, we put in our function, so in this case x to the 10 minus 1. You notice we're including that at x to tell it that this is that function call. We give it our starting guess, so 0.5. So starting guess. And then these options are coming from this line up here that would set those option values so that it shows, displays the number of iterations. So you can see display and then the number of iterations. And if you punch this out, you should see x equals 1 and f of x equals 0. So similarly to f of 0, MATLAB has some built-in power when it comes to polynomials. This is because many things engineers and scientists deal with tend to also be displayable or showable in terms of polynomials. And here we can say use the function roots, which will display the roots of a polynomial vector of C. So what does that mean? We need to build C first that's going to contain the coefficients of our polynomial. So let's take this polynomial down here, for example. So let's say f of x equals x to the 5th minus 3.5x to the 4th plus 2.75x cubed plus 2.125x squared minus 3.875x plus 1. I'm going to take the coefficient in front of each of those different x's and put them into this coefficient vector. So right in front of that x to the 5th, there's a 1. So that goes here. Next, we have negative 3.5. If I look at the x to the third term, it's 2.27. Put that in here, et cetera, all the way down to the value that is x to the 0 power is plus 125. That's that last value. All right, so here I have my C vector. I just call roots, and MATLAB will show what the roots are. So we can go backwards and determine the polynomial coefficients if we give it a root. So essentially, can we fit a function, polynomial function to roots? We can do that using the poly function. This is in essence going backwards, where if we put in those root coefficients, so this would be those roots, then MATLAB will return in B what those coefficients are in terms of this coefficient matrix, which is going to behave just the same as roots does, where it takes that first coefficient that goes in front of that x squared term, 0.5 goes in front of the x term, and negative 0.5 is in front of that x0 term. Lastly, we can keep going with this idea of using roots or polynomials to directly in MATLAB using the polyval term, where if I use that coefficient vector, so coefficient vector, I can pass different values to a MATLAB function called polyval, which will display the value of that polynomial at a given x. So this term in this example, a is that vector of polynomial coefficients, and 1 is the x that we're interested in. And in this case, we would get back out of MATLAB negative 0.25. That's going to round out our coverage of root finding methods. So at this point, you should know what an open root finding method is, particularly what the fixed point, how do you do the fixed point method, the Newton-Raphson method, the secant method, and inverse quadrature. You should also feel comfortable or knowledgeable, starting to get comfortable with using inbuilt MATLAB functions for finding our roots. Okay, see you in class.